Hi there, this is the first video of Chapter 8 where we'll talk about atoms and the way that they're constructed. So let's begin with some very basic components to atoms, and then by the time we're done with this video we should be able to construct a periodic table of the elements. Not the whole thing, but you know. Okay, so the first thing that we should look at is the components of an atom. There's the proton, there's the neutron, and there's the electron. These are the primary constituents of an atom. We have learned that these are made of even smaller pieces called quarks, or the proton and the neutron are. However, the electron is not made, as far as we know, of anything more fundamental. It is its own fundamental particle. Okay, so these things are relatively stable, and that's why we end up with atoms that are made out of them. So what we're going to do is talk a little bit about each one of these, and then we're going to start building atoms. Let's look at the mass of each one and the charge of each one. Now there are two ways to talk about the mass of each of these. One is in terms of kilograms, and the other one is in terms of something called the atomic mass unit, or AMU, the atomic mass unit. So let me go ahead and put that at the bottom of each one of these, and then you can see how that compares. The mass of a proton is 1.673 times 10 to the negative 27 kilograms. That is quite small. It is 1 billionth of 1 billionth of 1 billionth of a kilogram, a little bit more than that. So, quite small. The neutron, on the other hand, has a mass of 1.675 times 10 to the negative 27 kilograms. Now, for most of our purposes, we tend to view the mass of the proton and the neutron as pretty much the same, and as you can see, they are pretty much the same. They're very close together. Neutron is a little bit heavier, but for the most part, they're pretty much the same. The electron has a mass of 9.11 times 10 to the negative 31 kilograms, which is about 2,000 times lighter than even the proton. If we wanted to look at these in terms of the atomic mass unit, which is named according to the carbon atom originally, so it's not exactly that a proton is one atomic unit and a neutron is one atomic unit. They're actually a little bit off of that. A proton is given as 1.0073 atomic mass units, and a neutron is given as 1.0087 atomic mass units. See, slightly larger. If we wanted to look at the electron, well, my goodness, that is quite small. It is 0.00055 atomic mass units. Okay, so basically what you can see here is that you can count a proton as, and this is kind of how we'll label them, okay, is about 1 AMU, which we also refer to as a U. Like, that's 1 unit, 1 atomic mass unit. This is also, it's about 1 atomic mass unit. And this is about 0 atomic mass units. Okay, so it depends on kind of what you're going about calculating. In some cases you want to be very, very precise, and when you're going through basic calculations, you really are only interested in counting the mass of atoms based off of how many protons and how many neutrons they have. Okay, so let's look at the construction of an atom now. Let's go ahead and build a hydrogen atom. So if hydrogen is made up of a single proton and a single electron, and the way that we're going to build this is according to the Bohr model. So I'm going to write over here Bohr model because it was designed by somebody named Bohr. It may seem a little bit simple right now, but it turns out Bohr was quite genius. And at the time, we didn't have any idea about how atoms were built. And so, if we built a bunch of atoms, there were a lot of people who felt like this is the way atoms are built. They're built like perhaps like a blob. They called it the plum pudding model, but since this is the United States, that doesn't necessarily make a lot of sense. And so, I would prefer to refer to it as like a sort of like a fruit jelly model. So the fruit jelly model is that we have this like piece of jelly with these little bits of fruit in there. And their idea was that basically there's this sort of positive gel that's in here with these little bits of negative fruit interspersed throughout it, or something like that. There were all these arguments that were, about how these things were constructed, and then it would just sort of be mashed together with the next bit of gel. So we were trying to figure out what exactly atoms looked like. We knew that they all had the same kind of properties, but we didn't know what those were necessarily. And it was someone by the name of Rutherford that tried out. We can't see these; they're quite small. So what he did was he fired these little, basically bullets at them that we call alpha particles, and he didn't necessarily know what alpha particles were made of either. Now we do, but at the time he didn't necessarily know that. They're just very, very energetic particles that are like little bullets. He fired it at these objects that he thought were like jelly. And so he wanted to know, if I put a detector over here, then how do these things go? What do they do, right? And so he's studying the way that these atoms kind of play out over here. What does it look like over here? Do most of them land right here, or right here, or right here? So keep in mind that his context was, hey, this looks like jelly, right? And so I'm just going to fire my bullets through this jelly. He called it the equivalent of tissue paper. And then one of his students accidentally actually, I think Rutherford was the student that accidentally put this detector over on the wrong side. He accidentally put the detector over here, and started getting some readings. And so they worked for quite some time trying to figure out what was going on before they realized that these were real readings, and that firing these bullets at this sort of tissue paper, they were bouncing back. And he said this is the equivalent of firing a bullet at a tissue paper and having it bounce back. He was very shocked, very surprised by it. And this is what Bohr took hold of and said, you know what, I think I have an idea. He said, what if the things that they're bouncing off of are these hard particles in the middle? Since alpha particles are positively charged, they would be bouncing off of these hard particles in the middle. And then the rest of the atom really just is around that. So he took some other ideas, and said, I have another idea. What if the electrons are only allowed to be in certain places? So this is the way that he constructed it. And he said that these electrons are only allowed to reside in certain seats at certain levels, where this is the first level, and the level 1, and this is level 2, and this is level 3. And that it sort of was like a planetary model. Now, we know now that this is a little bit simplified for how atoms are, but it still serves as a pretty decent description. And so, yeah, it's fine. We can use this. Okay, so we have two seats that are available here. I'm going to write this as a box. On the n equals 1, we call n is the level that that our electron is capable of being at in the atom. So we have the first level is n equals 1. And then we have n equals 2 is the second level. Well, we have, we have, and this, again, this is a very simplified model. So we can address a a little bit more subtlety to this later on. Let's see, we have 8 seats on the n equals 2, and then we have even more on the n equals 3. There are actually 18 seats available on the next layer. Okay, now we're generally not going to run into too much trouble up here with a hydrogen atom, but let's look at, I'm going to get rid of a lot of these boxes because I don't want you to feel like I'm going to get rid of this whole third layer of boxes, and we're really going to just kind of play around with the idea of the n equals 1, n equals 2 boxes, and then we can just keep n equals 3 as a ring because there's so much of those there, and I don't like it. Okay, so we're going to place our electrons here in the n equals 1 and n equals 2. So for the hydrogen atom, we can say we're comprised of how many protons? Number of protons is equal to 1, and then we can say the number of electrons is, I'm going to put this in parentheses because we expect there to be 1. It's totally possible that you can actually fudge this by saying, you know what, I'm going to take an electron away or put one. They're like electrons put on a shelf. You can take them on, or put them on the shelf or take them off the shelf. But the proton is stuck there. That's just sitting there in the middle. Okay, so number of neutrons, well, there aren't any. 0. Okay, think about this in terms of that we have a proton with a positive charge here, and then we have an electron with a negative charge. So let's place our electron right here. Okay, and if we have an electron and a proton, you can see that since they're opposite charges, they're going to attract to one another. But essentially, because this is attracted, think about it like this is the sun and this is a planet. So this planet or electron is actually going to be circling around the nucleus in such a way that it never falls into the nucleus. It's in some kind of stable orbit there. Now, all these other seats are empty for now. It is possible, though, that we can take our let me go ahead and put this, I'm not sure why that happened. We can take our positive charge here, leave it there, and then we can pop our electron from one shelf to the next shelf. Now the first shelf only has two buckets on it, but the second shelf has 6 possible buckets we could place the electron in if we wanted to. So we'll place it in this bucket up here. And what happens is that when this electron is brought from this level to this level, the energy is it takes energy to lift it from the bottom shelf up to the next shelf. And you can kind of think about this as energy on a hill when you have like a sled on a hill and you had potential energy at the top of the hill, and then you have potential energy, not very much potential energy toward the bottom of the hill, and then at the bottom of the hill there's 0 potential energy, right? So you can think about it like this. As the electron goes up to the n equals 2 shell, it's been given energy to get there, and when it falls back down to the n equals 1 shell, then it has to release energy. Now this is very interesting. We'll talk about the way that it releases energy later, but for now what you should pay attention to is the fact that this energy at the bottom here, it can't go any lower than that. So this bottom shelf is what we call the ground state. When we have put for hydrogen in the ground state, it is in the n equal. There's 1 electron in the n equals 1 shell. Now, there's another way that we could look at this. Remember, if we take the electron and we take away an electron, well, all you have there is a proton left. It's not really even an atom anymore because hydrogen is special in that way. If you add an electron, then we can count up our electrons. So let's say we add an electron. So let's take an electron and let's put another electron on the shelf. And let's take a look at what that means electrostatically. Before, if you took a step back and looked at your atom, then the total charge of your atom would be you'd have here -1 for the electron, and you have +1 for the proton. But now that we have an extra electron, we've made this now, it's no longer -1, it is now -2. So the total charge then is going to be the total charge Q is equal to -1 for our entire atom, because it's a +1 plus a -2, right? And so then we have a total charge of -1 unit of charge. And that unit of charge, remember, that's that 1.6 times 10 to the -19. It's that fundamental charge unit. So we're just counting fundamental charge units here. It's a little easier to keep track of that way. Okay, so now what's the mass? Well, the mass of our hydrogen atom is basically 1 atomic mass unit. Yeah, like I said, a proton is a little off of that, but for the most part, the proton is basically 1 atomic mass unit, and the electron is basically 0 atomic mass units. So no matter whether we add the extra electron or not, the mass of this is going to be 1 atomic mass unit. Now, let's go through this whole process again, but this time let's create the next atom in our series, which is going to be the helium atom.